Hi friends, so today we'll continue the differentiation from yesterday's lesson. We have actually learned till the differentiation of exponential function and logarithmic function through first principles. Even trigonometric differentiation also we have done. So that knowledge we have to use in subsequent sums. Today we would like to go towards some operations of this differentiation like product rule, chain rule, then a division rule, that is a quotient rule. So such rules and all we'll learn today and do some sums. Also, we'll try to touch upon composite functions and differentiation of the same. So let us quickly revise yesterday's formula, what we learned. Go to the whiteboard. Yeah. So far, we learned that differentiation of x to the power of n is given as n into x to the power of n minus 1. So we have to only check here for x what power is there and use this rule. You will get the answer. By, let us say I'm having example, x cube is there. So you can write this as 3 into x to the power of 3 minus 1. That means 3x square. 3x square. If we are having, let us say root x. So again, root x stands for x to the power of half. So half is the power here. Then half into x to the power of half minus 1, which means half into x to the power of minus a half, nothing but 1 by 2 root x. X to the power of minus half is nothing but 1 by 2 x to the power of half. This can be written as 1 by 2 root x. So root x differentiation is 1 by 2 root x. So we can apply like this the formula. This is called power formula. Another one we learned in the trigonometry side. D by dx of sin x. This we learned as cos x. Then d by dx of cos x we learned minus sin x. All these things you write down and then remember in your notebooks because you have to use them in the sums. D by dx of tan x. This will become secant squared x. So other trigonometric ratios and differentiations you have to practice and then use the formulae in wherever they are required. Like all the time, there's no need for it to derive from the first principles. You can remember sin x differentiation cos x. Straight away you can use in the sum. Whenever you encounter a particular function sin x square, then cos x square you can write down the differentiation when you're doing. Okay. Now log x. Log x also we have done yesterday. That is nothing but 1 over x. Then e to the power of x also we have done. That is nothing but e to the power of x itself. Then we ended it with d by dx of e to the power of x, which we concluded as e to the power of x log a. So these are the basic things what we did. We have to use this knowledge in our further sums. There are certain rules we have to follow when we are doing the differentiation. Let us say, let u and v be two functions. There are, let us say, two functions. Now we are operating on that u plus or minus v. That means I am adding or I am subtracting u plus or minus v. I want to do the differentiation of this u plus or minus v whole dash. Remember, this dash symbol stands for differentiation. U plus or minus v whole dash is nothing but u dash plus or minus v dash. Suppose I am having another one called as product of these two functions. Then again, the differentiation of this product can be written as first function, that is u differentiation of first function into the second function plus differentiation of second function into first function v dash u. This is u. Okay. Next, third one, division. If I'm having a division of these two functions, then denominator into differentiation of numerator, that is u dash, minus numerator into differentiation of denominator divided by denominator square, where v is not equal to 0. So denominator into differentiation of numerator minus numerator into differentiation of denominator divided by denominator square. So remember this. These three are very, very important in the sums. Let us say, for example, I am having one sum. I'll do here and show you. Applying the first rule. 2x plus or minus x square. Let us, I am having this straight away with respect to the top first rule. U is equal to 2x. V is equal to V is equal to x square. So u plus or minus v will become what? 2x plus or minus x square. So now I want to do the differentiation. Will become 2x differentiation. That means 2x dash I wanted to calculate. Then x square dash. What is 2x dash here? 2 into what is x to the power of 1? 1 minus 1. We will apply the formula power rule what we learned. So 2x dash means here, I'll put in bracket so that you will not get confused. Yeah. So now differentiation of 2x whole dash. 2 as it is, x power is 1. 1 into x to the power of 1 minus 1 plus or minus 2 into x to the power of 2 minus 1. So this will become 2 into 1 into x to the power of 0 plus or minus 2 into x to the power of 1. So our final answer is 2 into x to the power of 0 is also 1 plus or minus 2x. So 2 plus or minus 2x. This is the answer for this. 2x plus or minus x square. 2 plus or minus 2x. Hope you followed this. I applied the first one. Now we'll apply second formula. What is our second formula? Product. So we'll take two functions. Let us say we are having x to the power of 3, u is equal to, v is equal to, you are having, let us say, x to the power of 2. Then I want to know uv whole dash. How do we do? Differentiation of first function into second function plus differentiation of second function into first function. So u dash, first function differentiation. So d by dx of x cube into v plus v dash d by dx of x square into u. What is u for us? U is nothing but x cube. So this one I'll write very close to this d. Yeah. So since I used notation v here, v stands for x square. That also I'll change it to x square. Now, what is d by dx of x cube? 3 into x to the power of 3 minus 1 into x square plus d by dx of x square. 2 into x to the power of 2 minus 1. This is as it is. So here 3 into x square into x square, 2 into x cube. So finally, 3x to the power of 4 plus 2x to the power of 4. This stands for 5x to the power of 4. So this is the answer. See, now here I will tell you one important thing. Let us say you have directly multiplied this. uv will become x cube into x square. So you know this is equal to x to the power of 3 plus 2, that is x to the power of 5. So differentiation of x to the power of 5, if I ask you, you know what it is. 5 into 5x to the power of 5 minus 1, which is nothing but 5x4. So matching now here. Straight away I multiplied and got this also. This way also we can do. But we are now applying the rule for the simple sum so that we will get to know clearly the rules. Because these are useful in the complex problems. Let us go to the next division rule. That is, let us say u is equal to, we are having now this time x to the power of 7, and v is equal to, I am having x to the power of 2. What is u by v for me? U by v differentiation I wanted is equal to denominator into differentiation of numerator minus numerator into differentiation of the denominator divided by denominator square. So let us solve. V stands for now x square, d by dx of x to the power of 7 minus u means x to the power of 7 into d by dx of v stands for x square, whole thing divided by v square. V square nothing but x square whole square is equal to x square. Now we'll simplify. D by dx of x7, nothing but 7 into x to the power of 6 minus d by dx of x square is nothing but 2x divided by x to the power of 4. So here x square, x6, theory of indices, this will become x to the power of 8. So 7 x to the power of 8 minus, here x to the power of 7, x to the power of 1, again x to the power of 8. So 2 x to the power of 8 divided by x to the power of 4. 7x8 minus 2x8, you can subtract. That becomes 5x8 divided by x4. So 5x8 divided by x to the power of 4 is nothing but 5x to the power of 8 minus 4 or 5x4. Okay, so even if you do directly, you will be able to get the same answer. You can cross check at home. Now, next one. Let us understand definition of composite function and do one sum on this and then conclude. What is a composite function? I will explain in by taking an example to you so that it will become easy. So let us say I am having f of x square, a function. G of x, I am having x plus 1. Now, if u of, let us say, x is a composite function defined from f and g. How? Let us say f circle g of x. So u of x I am defining now f circle g of x. So this is a composite function. How does it look like? Let us see. F of g of x it is called, or f circle g of x. It should be written as now like this. F of g of x. That means f of, what is g of x here? X plus 1. Now In the place of f of x square, our original function is f of x is equal to x square. Now in the composite function, we have to put x plus 1 wherever x is there. So therefore, we have to write here our original function f of x plus 1 whole square. This is our composite function now. This is our composite function. What is, let us say one more composite function I'll define, opposite. G circle f of x. This is nothing but g of f of x. Okay. Here, this means g of x square. G of, because f of x is defined as x square. G of f of x means we have to write whatever value we defined in the top. X square is there for f of x. So here, Vx became now g of x square, whose value is, what is g of x for you? Actually, x plus 1. So wherever x is there, we should write x square. That becomes now x square plus 1. This is called v of x. So now see the difference. Composite function ux, when you defined as f circle g here, we got it as x plus 1 whole square here. Correct? Here I am writing that becomes x plus 1 whole square. So here, when you define from ulta, that is the inverse side, g circle f, we got it as x square plus 1. So both are not same. So f circle g of x is not equal to g circle f of x. Only one particular condition like identity functions they call, that time if this is inverse of that function, both may match. Most of times. Here, only under special conditions it will be equal. That we'll discuss later. Under special conditions, I'm writing here, f circle g is equal to g circle x, g circle f. Only under special conditions, not all the time. So composite functions will be looking like this. If we do one sum, we'll get to know very clearly what it is. So let us see one sum. Differentiate x cube plus 2 whole square. Let us say this is the function I gave. This is a composite function for us now. So how do we do? First we do for the power. So d by dx of x cube plus 2 whole square is equal to 2 into d by dx of x cube plus 2 into 1 second, just 1 second. Here, some mistake happened. Yeah. D by dx of x cube plus 2 whole square. So answer for this is 2 into x cube plus 2 whole to the power of 2 minus 1. Like for power, we'll do it the same way. Then d by dx of x cube plus 2. So this is another function. First for the power we have done. Next for the internal function we are doing. That time we should not write any power here. So 2 into x cube plus 2 whole to the power of 1 into d by dx of x cube. That is nothing but 3x square. D by dx of 2. 2 is a constant number which doesn't vary. So differentiation of constant is always 0. So this will become 2x cube plus 4 into 3x square. This is the answer. Or you can simply take 2 common again, or 6 into x square into x cube plus 2 also you can write down this, because top one here function 2 into 3 6 will become 6x square x cube plus 2. Followed now. So for example, let us say one more sum I'll do, last sum for today. Differentiate sine x square. So how do we do now? D by dx of sine x square is equal to, first for sine x square we have to do cos x square, then d by dx of x square. So before sine angle is x square, for x square we should do, so this is cos x square into 2x into cos x square. So this actually is called as, sometimes we call it as chain rule. This is only called chain rule. First we have to see for the power, then we have to do differentiation for the internal function with the whatever knowledge we had learned in the previous lessons. So this is how we can carry out. So friends, hope you are following this. In the next class, we will do some more sums on based on this chain rule and product rule, etc. And then we'll go to the inverse trigonometric functions and parametric differentiations. Slowly, one by one, we will cover the topics. Okay. Thank you.